Michael.
Hello, how are you?
I'm good, thank you. How are you?
I'm good.
Okay, so
Okay.
hello everyone. Welcome to this week's Crunch seminar. This week we have two talks, very interesting ones. And before we begin with the talks, I would like to tell all of you that we have a Crunch group on YouTube right now, which is grouped as Crunch Group, the home for Maths plus X. I would ask you all to subscribe to our channel where you would get regular updates from our group. Now, let's begin with the talks. Our first talk is from Michael. He would be talking to us about reconstructing the pressure field around a swimming fish using physics-informed neural network. Michael is a second-year PhD student in the Fluid Transport Lab at the Johns Hopkins University. He received his bachelor's and master's degree in mechanical engineering from the Manhattan College and was awarded the Dean Robert Roy Fellowship from the Johns Hopkins School of Engineering. His current research focuses on studying resilient biological systems such as fish schools, which efficiently operate in a noisy, turbulent environment and effectively avoids various external threats. Through experiments and data assimilation, Michael seeks to better understand the hydrodynamic and social interactions that drive a fish motion and will demonstrate today how pins can be a useful tool for him to achieve this goal. With that, we welcome him.
Some data, are you recording this? I didn't see it. Are you recording it?
Yes, it's getting recorded.
Okay.
Okay, now let's make sure I can get this showing correctly. We're good?
No, you need to swap your, yeah, this is good. Perfect.
Okay. Okay, thank you for that introduction. So again, my name is Michael Calicchia and I am a PhD student at Johns Hopkins University. I work under Ray. And today I'm going to be talking about a method for reconstructing the pressure field around a swimming fish using the physics-informed neural networks that has been developed here at Brown University. So I'm going to break this talk into two main parts. The first part, we're going to talk a little bit about the motivation as to why we want to be able to resolve the pressure signals around the swimming fish. And in the second part, I'll talk about this pin-based method and applying this method to various simulation and experimental data sets. And I'm also going to give a little bit of a comparison to the methods that have been previously used by the biology community to kind of reconstruct the pressure field from velocity measurements. So first we'll start talking about like the general scope of this project. And so the idea is to study large-scale fish schooling behavior. And the reason for that is because fish schools can be thought of as a resilient biological system consisting of many simple individuals that can collectively work together to efficiently achieve tasks needed for survival, such as feeding or mating, or in this particular video, avoiding external threats and trying not to get eaten. So in this fish school, in the Maldives, you can see that sharks are making their way through the school, but yet the fish are basically deforming in such a way and basically opening up to avoid a minimal loss of life. And so it's going to be one of the things that we're interested in seeing is how at the individual level, fish are sensing signals that give them, that tell them that there is a threat, and how this collectively eventually evolves into this collective motion of the fish school basically deforming out of the way.
Michael,
so
can you play the movie again? Can you play the movie again?
Yep. I should have looped it. Right, so we see this, and then there's this big settle rush of the sharks, and the school is kind of just deforming out of the way and letting the sharks kind of pass through. So this is one example where there are both visual cues that the fish see. They actually see the shark, and they're also sensing the hydrodynamic signals of this pressure wave as the sharks pass through. And so we also see another example where they don't need to necessarily have visual cues to kind of deform and sense that the threat is coming. So in this particular video, a man is coming up and kicking at the school, and you see that the wave is approaching. The school kind of deforms as they feel that wave, and then when that kind of cools down, they come back to that steady state kind of form. So we're really interested in seeing, how are fish actually responding to the various different hydrodynamic signals that they sense in their day-to-day lives. And the reason for this is because you can use the knowledge learned from this biological engineering system and to use that knowledge in the development of our own engineering systems. And in particular application can be swarming of autonomous underwater vehicles. And I think there are about three main categories of concepts or knowledge that you can learn from studying fish schools that can be applied to such systems. The first is that, as is shown in the videos before, they have an ability to detect and avoid external threats and harsh environments. So if we can learn those principles and apply them, and then ultimately apply them to our own engineering systems. The other thing that we can note is that each individual fish is constantly sensing various signals, responding to those signals, interpreting those signals, and then formulating an efficient behavior based on what they're sensing. We also know that the information gained from certain signals of an individual fish is then transferred to nearby neighbors to give rise to this kind of collective behavior. So if we can understand how individual fish are receiving and processing this information, responding to it, and then transferring that information to other parts of the system, we can use that in our development of our own engineering systems. And the last thing is that there's evidence that suggests that there's hydrodynamic benefits of swimming in a group. So there's many studies that show the cost of transport of a fish decreases when they swim in a school as opposed to being in the individual. And then one of the things that we're going to take a look at is actually see if fish schooling is a mechanism for fish to deal with high levels of turbulence. So one of the hypotheses that we have is that the school can actually work as a filter and kind of eliminate the extra noise that is found in these hydrodynamic signals in heavy turbulence and get those signals to be more coherent so that they can properly respond to those signals, they can properly sense those signals and respond accordingly. So like I mentioned earlier, we're really going to be focusing on the hydrodynamic interactions. And that's because there's quite a few examples where there's changes in fish behavior in the absence of visual cues. So one of the things is that it's believed that fish can sense the pressure difference on either side of their body. And they can use this information to kind of align themselves with the oncoming flow. So in this particular sense, this fish is at an angle of attack about -10 degrees. It will sense the pressure difference on its body and knows that it must turn to kind of align itself with the incoming flow. So this is one example. Another example that we've observed is that if I change the background flow conditions, there are changes in the kinematics of the fish. So in this experiment that we ran at Harvard, we exposed this trout to both laminar and turbulent flow, and the turbulent flow was generated by this gridded plate. So if we take that plate out, we see this kind of kinematic behavior of the trout. And when we put that plate in, we notice that the kinematics are changing. So now you have the whole body is deforming in this case, and you see a higher amplitude in the head region. So being able to understand what signals that a fish is sensing to then make them change their kinematics is something that we're going to be interested in figuring out. And the last example that I have is actually experiments ran by Ian Cousins' group, and they defined this concept of vortex phase matching. So not only do you see changes in kinematics when the flow conditions change, but you also see changes in the kinematics when you add another fish. So in this particular case, this phase difference exists in the tailbeat frequency to kind of decrease the trailing fish's cost of transport. So they're utilizing the vortices shed by the leading fish to kind of reduce their energy costs. So in order to study these hydrodynamic interactions, the first thing that we need to do is understand the system that allows fish to sense these flow properties. And so that system is known as the lateral line. And without getting into too much detail, this lateral line system can be used to not only sense velocity gradients in the flow when the flow is pretty much steady, but also interpret pressure differences in the flow, which fish primarily rely on in unsteady flows. And if you look at the distribution of this lateral line system across many different fish, which is what these different lines represent, you see that they all kind of resemble the same profile. And so what Richtroff et al. Had done in their 2015 paper was try to correlate this distribution of the lateral line system with properties that fish can potentially sense from the fluid. And what they did here is they basically calculated the pressure coefficient on the left and right side of the fish at a -10 angle of attack. And then they plot that profile along the body, and the dots and the lines just represent two different techniques for getting the pressure. But what they then do is plot this pressure difference profile, which you can see aligns very nicely with the distribution of the lateral line system. So this suggests that pressure and the pressure difference across the body is a property that fish can actively utilize. And so that is why we're going to be very interested in being able to resolve the signals that the fish are able to sense with their lateral line system. So in a general overview, what we really want to be able to do is perform experiments to study the hydrodynamic interaction in schools of fish ranging from 2 to 30 individuals. So we want to be able to not only understand like how this fish is responding to the surrounding flow, but also how it's responding to the perturbations caused by neighboring fish. And so to do this, we're going to need to have certain requirements for our experimental facility. And the first is that obviously it needs to be large enough for us to be able to study schools with a large number of individuals. And the second is that we want to have the ability to systematically control the level of turbulence independent of the mean flow. And this is going to allow us to basically vary the noise level and the coherency of the hydrodynamic signals that the fish are going to be able to sense. And we're going to see if there's a certain threshold where it just overwhelms their sensory systems, if schooling allows them to better handle these noisy signals, et cetera. And then what we want to be able to do is take the signals sensed by the fish and also record and measure their behavioral response, and then try to relate the two together. But to do that, we're going to need to intercept the pressure signal that is sensed by the fish's lateral line in a non-invasive manner. We don't want to basically obstruct the natural behavior of the fish. And this is where that so pressure reconstructions from, say, velocity data is something that we started to look at. And that's basically what the second part of this talk is going to focus on, and how we can use a physics-informed neural network to kind of do that for us. So before I get to that, I will just show basically the CAD model of our experimental facility. And so we'll have a flow being driven by this axial pump design on this side. Let me just change this to, okay. So we have this axial pump design here. The flow will basically come up through this inlet section and pass through our honeycomb before it reaches our turbulence jet array system. And in the top left, you can see a more detailed version of that, or a blown up version of that. So at the top, you see about 40 individual ports that will basically connect from tubing coming from this manifold. So they'll come out, go up and over and connect. If you look at the cross section, each of these jets are independent of themselves. So we'll basically be able to control or fire each independently using a system of solenoid valves. So we can get random patterns, different flow speeds in the jets. And that's going to allow us to be able to generate turbulence with a wide variety of scales, and see how the fish and the schools kind of respond to that. This will be observed through our test section here, which is about 50 centimeters wide, 70 centimeters tall, and about 200 centimeters wide. So it gives us enough space to study large schools and also let the turbulence become fully developed. And then right here, we'll have our exit where the water will rejoin the recirculation pipe and then come back around. This facility is going to be known as our FATE facility, which stands for Fish Aquarium in a Turbulent Environment. And just last week, we were able to finally fill this thing up with water and stop all the leaks, turn the pump on, and actually got some flow. So the next step is going to be to get this turbulent jet array system installed. And shortly after that, hopefully we'll be able to start taking some experimental data of our own. And so I would like to just thank the JHU Machine Shop for their help in design and assembly of the system, because it definitely would not have been where it is today without their assistance. So with that, now I do want to start, now that we have a general idea and motivation behind why we're trying to do this, I will now start to talk about non-invasive methods for intercepting the pressure signals sensed by a fish's lateral line system. I'll talk about I'll give a little overview of the literature, and then really highlight the particular method that the biology community is really using, and then explain why we feel the PIN method is going to offer considerable advantages over what has been done in the past. So this is by no means an exhaustive list, but you can basically think of breaking the pressure reconstruction algorithm into different categories. The first is that you would basically, all of them basically require you to basically measure the velocity field. The first category then takes that information and you will solve a Poisson equation for pressure using a numerical technique. As Sharonko et al. And Han et al. Had suggested, these Poisson solvers are typically very sensitive to the uncertainty in the velocity measurements. It's sensitive to the boundary conditions that you apply, and it's also sensitive to the shape of the immersed body. And as DeBerry et al. Suggested, when you're studying animal locomotion at moderate Reynolds numbers, sometimes it's very difficult to actually know what boundary condition you should apply at the surface of the fish. And so then they came up with, there's also this other category of pressure reconstruction techniques, which involve integration of the pressure gradient field. And this is typically done through a multi-directional approach. This is also the category that the biology community typically uses, and that's this DeBerry et al. Paper. So I'll be talking a little more detail about these multi-directional integration techniques in a little bit. And then more recently, we have these like optimization and data simulation approaches. And I've thrown in, some of these other PIN studies that you guys have been doing, because in reality, you're taking measurements of some property in the flow field, and then using the PIN, you're able to recover the pressure field. So we're trying to do a very similar thing with that. And so we'll talk about how the application of that in a little bit. So first, let's give a little overview about the Queen 2.0 algorithm, which is that DeBerry et al. Method that makes use of the multi-directional integration scheme. I'll talk about it, then we'll talk about its limitations, and then we'll talk about how PIN can basically overcome those. So the first step is going to be to obtain the 2D velocity field around the fish's body using traditional PIV techniques. And then the second step would be you'd have to compute the pressure gradient field. And to do that, you would need to approximate the material derivative, which is done through a pseudo tracking approach that makes use of finite differencing. And you'll have to approximate what the viscous terms would be. So you would need to do central differencing to kind of approximate that. And then to get the pressure, you basically integrate from the boundaries along multiple different paths to get the pressure at a particular point. And so the reason that they will integrate across multiple paths is because of the fact that pressure is a scalar property. So it should be independent of the path that you take. And so what ends up happening is that you can get 8 different, in this particular scheme, you'll integrate from the top, the left, the right, the bottom, and the diagonals to get about 8 pressures here. And then you'll take the median of those pressures to be your true pressure value so that you can mitigate the amount of error or noise or uncertainty that have been propagating from your velocity field into your pressure reconstruction. Now, the downside of this approach is that in order to do this integration, you have to know what the pressure should be at this external boundary. And so for this particular method, what they do is they assume that this is all zero pressure. The homogeneous boundary condition on the edges, which is not always necessarily accurate. There are other methods like by CATS that first guess the boundary condition and then continually iterate and updating the boundary condition for the pressure. But it's important to note that this DeBerry et al. Algorithm took all of that out to kind of cut down on the computational expense. So they sacrificed a little accuracy for the computational expense to save on the computational expense. But in addition to that, there are some limitations to the algorithm that could become quite burdensome when you actually try to apply this in principle. And the first is that the surface pressure is not directly computed in this reconstruction. In order to get the surface pressure, you would have to extrapolate from the reconstructed pressure field. And they do this for 2 reasons. The first is that if they did want to resolve the pressure field all the way to the body, then they'd have to make use of deforming grids. And they'd have to and then it becomes a lot more complicated to do the finite differencing at the grid where the body is deforming. And so to avoid that, they don't even consider it. The second reason is that the PIV data closest to the body becomes less accurate. And so to avoid that uncertainty or error from propagating into the pressure of reconstruction, they basically only go up to points furthest away, the closest point away from the body that doesn't intercept the actual body. So there are there were potential issues with this. In a recent study by Ernie et al. In 2020, they showed that if you don't enforce the kinematics of the body in your pressure reconstruction, the surface pressure prediction tends to become less accurate. And so when we would need to have a technique that allows us to easily incorporate the kinematics of the body into the pressure reconstruction to improve the accuracy of the prediction, which this Queen algorithm does not have the capability to do as of yet. The second thing is that if the velocity data is inaccurate near the body, maybe we should have a means to correct that velocity data as part of our pressure reconstruction. So now we get to fix the velocity and also get the pressure field, which again, this algorithm does not have the ability to do. The second issue is the one that we've talked about. This homogeneous pressure boundary condition applied on all sides may not necessarily be accurate. So for example, in this particular case where you have the vortices that are being shed by the beating tail crossing that right boundary, the zero pressure boundary condition is not applicable. And so how much error is that going to introduce if you enforced it anyway? And then the last thing is, what happens if I had multiple bodies in my domain, which is something that we're going to want to
Michael, for this middle, because the very simple, you can change, let's say in the wake, instead of P equals 0, you can, from the Navier-Stokes equation, you can get dPdN equals the minus of the curl of omega dotted with n. So the curl of V dotted with n is an exact pressure boundary condition that you can apply.
And you apply it directly.
Yeah, and then of course, because if you have the velocity field, you can, of course, get the vorticity, and then you can get. So that's a Neumann boundary condition, but it's an exact boundary condition derived from the Navier-Stokes. I use that in my solvers actually. I developed it in 1991, and that's actually works really well. Also for the wake, you can take into account also the time dependence. So that probably an easy fix there.
Yeah. I mean, so that is an alternative to use. They're just not applying that in this particular method. They just leave it as 0 regardless of what it is. But that could be a quick modification to their code.
Yeah.
To allow it to increase its accuracy. I see what you're saying.
Okay, go ahead, please.
Okay. So the other part of this is that what happens if you had multiple bodies in the flow? And so if you were doing this integration from the boundaries and then terminating the path at the body, you won't be able to get, say, all 8 paths in between the two fish because their bodies will be blocking it. So you might be able to get the left and the right path, but the diagonal top and bottom paths, you might not be able to actually get to the points in between. So therefore, the error in the pressure in between could be increased. And therefore, the pressure on the body, on the left and right side of the fish in these cases, will also be increased. And so to kind of correct this issue of having to integrate from the boundaries, we figured that reposing the problem as an optimization problem could become very useful. And so, for example, again, you'll have your spatial and temporal coordinates, and you'll predict your velocity and pressure fields. You know what the velocity field should be because you've measured that, and then you can recover the pressure field from your governing equations and the applied boundary conditions. So that this provides us with the ability to use the PIN framework to be able to do this minimization process and recover the velocity and pressure field. The same PIN framework that you guys are well aware, so I don't need to go into the details here. But I do want to highlight 5 distinct benefits that we feel the PIN framework provides us over what is traditionally have been used. And the first is that the automatic differentiation that's involved eliminates the dependence on the finite differencing. And this is going to allow us to basically enforce the fish kinematics with pretty easily, without any need to have any deforming grids or anything like that, because you're not necessarily setting up this Cartesian grid. Your inputs are basically a large vector of your spatial and temporal coordinates. The third thing is that we can compute the surface pressure directly on the body. There's going to be no need for extrapolating from the pressure field, because once we have this trained network, we can evaluate pressure at any x, y, t point. Because we're also solving for the velocity field in addition to the pressure, we can correct the velocity near the body if we find that the experimental results are not necessarily satisfying the governing equations. And the last thing is that we have the flexibility to apply proper boundary conditions, because we're not integrating. So if we don't necessarily know the boundary condition at the external boundaries, we don't necessarily have to enforce one, since we're not integrating from the boundaries. And if we do know them, then we have the flexibility to just apply them as we've done in the past.
I have a question, because we have these questions ourselves. At the boundary, what do you do for the velocity boundary condition? Do you set it to 0 for the field of the flow, or is it actually the moving? You have the moving boundary, and therefore you set it to moving, but you allow it to slip or no slip?
It is so that, yeah, so basically this, we don't apply any no slip on this body.
You
The
don't
only thing
apply any boundary condition.
The boundary condition that we've enforced on the fish is, which I'll get to, is just the normal velocity.
Just a normal velocity, nothing on this. So actually you allow it to slip then?
Yeah.
Okay, yeah.
Okay, so what we've done here is we have a DNS data set of a swimming fish, which was done by Dr. Seo and Dr. Mittal from JHU. And what we do is we're basically going to take a slice out of that data set along the midline of the fish's body. And this plane will contain the velocity gradients and the pressure signals that the fish's lateral line system should be able to sense. And there's two reasons why we use the a 2D plane out of the 3D data set. The first is that traditionally in the studies that are performed of this kind of animal locomotion process is usually done in 2D. So we want to give a pressure reconstruction technique that can be suitable for 2D flows. And the second reason is because that Queen 2.0 algorithm is primarily for two-dimensional flow, and we want to be able to do a direct comparison to that method and see how PIN's performance compares with some of the techniques that are currently out there. And so when we do that, there are some modifications that needed to be made, or assumptions that need to be made when we enforce the governing equations in those Navier-Stokes residuals. For starters, because it's a 2D slice out of a 3D data set, we're not going to enforce the continuity equation. And the second is that the W terms and the DDZ derivatives that we have are going to be assumed to be negligible. So really, what we get is our X and Y momentum equation make up our Navier-Stokes residuals, and the continuity equation is not enforced. So we do know, or we do expect to see that when the flow is highly three-dimensional, we're going to have an increase in error in the pressure reconstruction. But both the Queen algorithm and the PIN would suffer from that same assumptions that were made. So now we'll talk about like what kind of constraints for the data and the boundary conditions that we are applying here. For this particular simulation data set, the PIN will know obviously the velocity field at all spatial and temporal coordinates. We also gave an inlet velocity boundary condition to show flow is going from left to right. And then because the upper and bottom boundaries are so far away from the fish's motion, we did enforce that zero pressure boundary condition at those points. And on the right boundary, we just left that as is. We didn't enforce any boundary conditions there. To enforce the kinematics of the body, we basically compute the normal velocity on the body of the fish, and then we allow, so we're basically enforcing a non-penetration boundary condition, and we allow the PIN to learn what the velocity normal to the body should be at those points. And when we train the network, we end up with predictions that look like this. So the top is the DNS 2D slice for the velocity and the pressure field, and the bottom is the PIN prediction for the velocity and the pressure field. And we can see that for the velocity field and the pressure, there's a good agreement, at least qualitatively, between the PIN prediction and the DNS results. The only slight differences could be found in the pressure, where maybe the amplitude is slightly different, but at least the features of the flow appear to have been captured. If we look at a particular times, if we look at an instantaneous pressure field predicted by both the pin and the Queen 2.0, we'll get something that looks like this. So this top one is the DNS data results. This is the pin prediction, and this is the Queen prediction. On the right here is basically the absolute error between the coefficient of pressure predicted by each of the methods and the DNS data set. We can see that for the majority of the body, where the body is pretty much stationary, there's good agreement between the pin prediction and the DNS results and the Queen prediction. But as we get closer towards the tail region, we start to see some discrepancies between what the Queen algorithm is predicting and what the pin is predicting. So where this arrow is pointing, we can see that the Queen is actually predicting a positive pressure on the tail, whereas the DNS and the pin results are showing a negative pressure. So there's this region of localized error that is going to be quite high for the Queen 2.0 algorithm. And we're attributing that to the fact that, one, now for the pin, the kinematics of the body is enforced, and two, the pin is predicting the pressure directly on the body, whereas, well, actually, and as where the Queen has to extrapolate to get close to the tail. But that shouldn't have affected this plot. That'll be my next plot. And so the other thing that we notice is in this wake region, there is these bright yellow spots in the Queen algorithm that are not necessarily seen in the DNS and in the pin. And that is attributed to the fact that this right boundary had that zero pressure boundary condition. So the multi-directional integration scheme was able to eliminate some of that error at certain points in the pin and the Queen reconstruction, but not at all points. So that's why you start to see these kind of spotty places, especially in the error field, where you have brighter blues. Whereas for the pin, it's more uniform because we didn't enforce zero boundary condition on the right side. And so we didn't introduce that error into the pressure reconstruction. So we've shown how basically removing that boundary condition and forcing the kinematics of the body has kind of improved the pressure reconstruction in terms of the field. But now what we want to do is also take a comparison between the pressure signals on the body predicted by each of the method and compare them to the DNS results. So on the top here, we're basically showing the pressure profiles on the surface of the body at two different time steps. This is one time step, this is the second. The red data is the left side of the body and the blue is the right side. The open circles are the DNS, the solid lines are the pin, and the dashed lines are the Queen algorithm. And we can see that, again, from the front part of the body, the surface pressure predictions by both methods are pretty consistent. And then we start to see larger deviations in the Queen algorithm as we get closer to that tail region. Discrepancies also exist, for the pin as we get closer to the tail as well. Whereas for the majority for the first part of the body, there's good agreement throughout. On the bottom, we're showing the difference in the pressure coefficient on the left and right side of the body, just because we saw from that first plot from Ristroff et al. Study that pressure difference is a quantity that fish can sense. We wanted to see how accurately we can recover that. In this case, the black circles are the DNS results, the solid red line is the pin, and the dashed lines are the Queen 2.0 algorithm. So again, pretty good agreement for the majority of the body, with the pin being slightly more accurate. But it is important to note that the spatial and temporal resolution of the velocity field in this case was the delta x was about 0.02 times the length of the fish, and the delta t was 0.02 times the tail beat period. This is the condition that Queen enforces such that you can get a proper or accurate reconstruction process. So we wanted to see how did the results compare as the pressure, as the resolution of the velocity field becomes coarser. And so when this happens, we're going to get plots that kind of look like this. So the top here is our spatial resolution study, where we fix the delta t at 0.02 times the period. And then we predict what the surface pressure is on the right side of the body at these different times, at these different resolutions. And we can see for this Queen 2.0 algorithm, as the delta x gets larger, which is these blue and green colors, this red is the finest resolution, the accuracy of the prediction becomes decreases. And you actually start to see just like straight projection of zero pressure at that point. And so part of this could be explained by the fact that the finite differencing methods that it rely on become less accurate as the delta X is growing. And the second thing is if you have to do extrapolate from the pressure field to the body, and that delta X is increasing, you're going to be extrapolating over a larger distance, and so you expect the error to decrease. For the pin framework, we see that the prediction on the right side of the body is less sensitive to the spatial resolution of the velocity field. And part of the reason is because when we evaluated the Navier-Stokes residuals, we evaluated those on the finest grids, not necessarily at the points where we had measured velocity data. So in essence, we were basically able to interpolate the given measurements in a way that's informed by the physics. And so that had proved to basically improve, that helped us improve the prediction of the surface pressure, even as the resolution of the velocity field decreased. And so on the right here, I'm basically plotting the root mean square error of every point on the body, the pressure on every point on the body compared to the DNS for all time. And we can see that for the majority of the body, for about 0.06 times L, the length of the fish, the pin RMS error remains relatively flat and then starts to grow after about that point. But the Queen algorithm is always increasing until it gets to about a maximum error. And so the same kind of trend can be seen if we fix the spatial resolution and vary the temporal resolution. For the pin, again, all of these profiles appear to be collapsing onto the same curve, suggesting that the pin is not really sensitive to the temporal resolution of the data set. But for Queen, when you get to the part that is really involving a lot of the motion, the error starts to rise, where it's just not really giving an accurate prediction as what the surface pressure should be. And that can be captured again in this plot on the right here, where the error and the pin kind of stays relatively flat, whereas the Queen algorithm rises as the delta T gets coarser and coarser. So not only have we shown how forcing the kinematics can improve the pressure prediction, and how not enforcing that homogeneous boundary condition will improve the pressure prediction, but we're also showing that the spatial and that the pin is less sensitive to the spatial and temporal resolution of the initial velocity field. So all benefits over the Queen 2.0 algorithm that is typically have been used. And so the next thing we want to do is actually apply this method to experimental data. And so this is an experiment run by our colleagues at Harvard, Robin and George, basically studied how a zebrafish is turning in still water, which looks like this. Right, so sudden motion and then a quick turn, and then it goes towards the boundary. So we want to see if we can use pin to kind of predict a pressure field for this particular case. And so just like before, again, when we create the constraints put forth by our measurements and our boundary conditions, obviously we know the velocity field, but this time we didn't enforce any boundary conditions at the external boundaries. And part of the reason for that was because of the fact that the fish is approaching kind of that top and left boundary during its motion. And so to make no assumptions as to what the boundary condition should be, we just left it off and wanted to see how well the pin performs without those enforced. And again, as before, we know the kinematics of the body, so we enforce them using this non-penetration boundary condition. And so when we do that, we get, again, results that look like this, where the reference is referring to the measured velocity field and the regress is referring to the pin prediction. And we can again see good agreement between the velocity field that the pin predicted versus what was measured. And on the right-hand side here, we can see the prediction of the pressure field by the pin framework. And so the next thing that we need to then study is what happens if we have two fish interacting now, and can the pin framework effectively handle this case, whereas for the Queen algorithm might give some issues. And so again, we do the same procedure where we take the 2D PIV plane, we take that slice out of the 3D data set. The boundary conditions applied were the same as for the single fish case. And once we do the training process, we get results that kind of look like this. Again, the top is the DNS results and the bottom is the PIN results. And we can see pretty good agreement qualitatively between the velocity and the velocity fields. And then the pressure fields also are showing good qualitative agreement with, again, just the amplitudes may be off in certain cases. So just like before, this not only do we want to recover the 2D pressure field, but also the surface pressure along the body. And so that's what we're doing here. Each column refers to the different time step. The top row is basically the pressure for the top fish, and the bottom row is the pressure for the bottom fish. Again, red is the left side of the body, blue is the right side, the open circles are the DNS, and the solid results are the PIN. And we can see that for the majority of the body, in this case, there's very good agreement between the PIN prediction and the DNS results. And even for the bottom fish, we can see that there is definitely interactions happening with the top fish as this pressure has dropped and then quickly rises when the overlap after that overlap point has been passed. And so we see that the the PIN is able to predict the interaction of the pressure or the perturbation in the pressure due to the top fish, just like the DNS was able to tell us. However, for this particular data set, I had given the PIN this kind of velocity field. But in reality, if you wanted to measure that in an experiment, even if you had like a 2 laser system where you can have the sheet overlapped from the back and the front, you'd still be missing this region in between the 2 fish. So a question that I had was how, if I trained the network on basically a velocity field that looks like something like this, I mean, obviously you won't have this data either, but if I trained it on something that looks like this, how does that affect the pressure prediction on the surface of the body? Can I give this this velocity field with missing data to the PIN and still get accurate answers, or is there something I have to do to kind of fill this space in? And so when we train the network on this kind of velocity field, we get plots for the surface pressure that look like this. So the missing data is on basically for the top fish is on the red side, right, and towards the back. So it's in this particular region. And we can see that we do start to get deviations from the surface pressure when that velocity information is missing. You see that at this time step, and also at this time step, there appears to be this like over approximation. And so and then for the bottom fish, we see that this blue curve has pulled closer or farther away from the DNS results. And on this side, we also see an increase in this blue curve. So the right side of the body and this particular region in the front of the fish is also missing velocity data somewhere in here. So the question is how can we, is there a way for us to potentially improve that result? And so the first thing that we did was basically say, what if I fill in the gap with an initial guess? What if I interpolate, I know my velocity data at all points, what if I interpolate from that to fill in this gap and try to train the network on this kind of data set where the space that's missing is now given some initial guess? Can the PIN correct the velocity and also give me a good prediction for the pressure? And so when we do that, we end up with pressure profiles that look like this now. So again, we can see this is for the top fish is the red curve that was primarily of issue. But now when we get towards the back of the fish, the pressure is returned pretty much following the trajectory of the DNS data now, instead of deviating off like it was before. And at the second time step, the same kind of trend is seen. Instead of deviating up and above, we pulled this now closer towards the DNS prediction. Same is again observed on the bottom fish. So this blue line was somewhere up here before, and now has been brought closer to our DNS results. And the same can be said about the pressure profile at the second time step. So now the question is then how did why did this come out? Why did basically giving an initial guess help the improvement in the pressure prediction? So what I did is I basically plotted a quiver plot of the velocity vectors in the region between the 2 fish. And the black arrows are the DNS results, and the blue arrows are the interpolated initial guess. And we can see that in this region, for the most part, they're pretty consistent, and then there's larger deviations as you get closer to that tail region on the top fish. So I wanted to see, well, okay, what does the pin prediction for the velocity vectors look like after, after the training process. And what we get is a plot that looks like this. So the red arrows are basically the output from the pin, but the velocity field output from the pin. And you can see that if you can't see that there are no more like black arrows. And so the pin is pretty much corrected the interpolated initial guess to really align closely with the DNS data. And that can be utilized to explain why the surface pressure prediction increased when you gave it some kind of an initial guess. The pin was able to correct that velocity field and thus recover the pressure, which again is another piece that this Queen 2.0 algorithm is not able to do. It's not able to correct the velocity. It can only give you pressure. But with the pin framework, we can get both. And so the next thing to do would be to take this multi-body kind of problem and apply it again to a real life experimental data. And so in this case, you have basically a flapper and a trout swimming in your flow field. And we want to be able to recover the pressure field around the trout. And there's a couple of reasons, and in particular, we want to be able to recover the pressure right in this region. Because what's interesting here is that the trout has the ability to swim at any point in this tank, and yet for some reason decided to sit right behind the flapper and stay there. So it'd be very interesting to see what kind of signals the trout is receiving that makes it want to, that is beneficial for it to stay in that particular region. And so if you try to do this with the Queen 2.0 algorithm like Robin and George has attempted, again, the paths, the integration paths from the left and probably these diagonal paths to try to get somewhere in between here will be obstructed. And so how accurate can you really take the pressure in between these two bodies to be? So we want to see what kind of pressure the pin predicts and compare that to what the Queen algorithm is giving us. So the last thing that I do want to mention is this notion of 3D effects, since we only did the reconstruction on a 2D plane. So again, because we were missing that third component of the velocity field, we didn't enforce the z direction of the momentum equation, nor did we enforce the continuity equation, right? And then we noticed that for both of these algorithms, there were a large error right around the tail. So this was the pin and this was the Queen and the Queen algorithm. So I did want to see if that had anything to do with the three-dimensionality of the flow field. And so to quantify that, what I basically did is I computed the residual of the continuity equation at various different time steps. So I basically did the du dx plus dv dy, and I said that should be 0. If it wasn't 0, that meant that the dw dz term was not negligible. And so in regions where you have the largest residual of the continuity equation, you would have pretty three-dimensional flow at that point. And so I looked at, okay, with the regions where the continuity equation is highest, does that correlate to regions where the error in the pressure reconstruction is highest? And for this particular case, on this left side is the pin prediction, and it's the error between the pin prediction and the DNS. And we can see that there are the highest, in regions where the residual is the highest, is also regions where the pressure reconstruction is the highest. So there is this limitation to this kind of framework where your flow is highly three-dimensional, that obviously your surface pressure or your pressure prediction is going to suffer because it's not properly constrained. And so to kind of deal with this fact, the next step would be to expand the framework to 3 dimensions, which has been done in the past. Whereas the Queen 2.0 algorithm currently is simply meant for 2D. So expanding it to 3D will have to would take some time in the development of that.
Michael, I have a question for you. I have a question for you, because you do have the 2D plane, but nobody constrains you from doing the 3D for pins. In fact, we have done that. We have published a paper in for the microfluidic blood flow in PNAS, and we have shown from a single plane you can get a 3D flow.
Yeah, so that is something.
As long as you know the boundary conditions for the velocity.
Right. Right, so that's also another step to see, like, if I have planes, if I have a plane, can I recover the 3D? Yeah, so that is also something that we can play around with to say if we can, because ideally the other thing that when we were thinking about like implementing this in experiments, if we did a 3D kind of reconstruction of the flow, what's the resolution going to look like of that, especially if there's multiple bodies sitting in the flow field. So part of it might be that we do a collection of planes and then use this framework to then predict what the third component of the velocity should be. So that is something that we're going to kind
That's true
of
here, because the body is moving. You need the 3D segmentation, if you like. At least for the body, you would need to have the 3D motion. But otherwise, the flow field, you can cover it.
Yeah, so flow field, like 2D planes and then 3D reconstruction of the kinematics is kind of what we were shooting for.
Right.
So with that, I just want to wrap up and kind of put conclusions on what we were talking about. So the main goal is to be able to understand how fish react to unsteady flows. And in order to do that, we need to intercept the pressure signals sensed by the fish's lateral line system. We've demonstrated how pins can offer a considerable advantage over the traditional technique, this Clean 2.0 algorithm. We've shown that it's less sensitive to the spatial and temporal resolution that incorporates the kinematics of the body. It can incorporate the kinematics of the body into the pressure reconstruction, which improves the surface pressure prediction. You have a flexibility to apply relevant boundary conditions, and the pin also allows a means to correct the velocity field near the body that the Clean 2.0 algorithm might not have had. And so we have submitted a paper on this work that is currently under review. So hopefully that comes back with good reviews and will be published soon. And then lastly, I would like to acknowledge everyone that I've had the opportunity to work with so far during my PhD, and also thank the Office of Naval Research for sponsoring this project, and also our Rockfish Computing Core facility, which is where the pins were trained on. And so with that, I would like to say thank you again for having me, and I will be happy to answer any questions that you have.
Thank you, Michael. That was wonderful.
Hi, it's Xian. I'd like to ask a question about the setup of your pin.
Okay.
Yeah, thank you. So in the pin, how many data points you choose for your doing regression? I mean, the U and V you choose from the DNS.
Yeah. So one thing I should have mentioned is that we've reduced the resolution of the DNS data set.
Yes.
Right. So we cut that down, and then like at each iteration we sample 10,000 of those points.
So you mean that's
the loss function.
So in each frame you choose 10,000.
Well, the whole frame, so the entire reduced spatial resolution and all those time steps are given to the pin to train with.
Oh,
and out of that, we subsample 10,000 of those points every iteration to evaluate the loss function.
Okay. And how many points you've used to compute the residual loss?
As in, like for the loss term?
Yes. How many
it's
points?
It's the same number of points.
Okay, thank you.
Qian is doing the work of the COP mod.
Yeah, quite similar to yours actually.
Gotcha.
Yeah, you present a very thorough study. I like your resolution studies. I like the GAPI data was interesting, and yes, the pins will respond well if you start with something reasonable, because the landscape becomes the optimization landscape becomes simpler. One idea that I could suggest here, because in PIV you don't have regular points, you can use kriging for interpolation. kriging is the best way of interpolating any data. So you cannot beat that with any other interpolation. So basically, kriging would take all the data surrounding this region, would construct a kernel, and then you can use that same kernel to fill in the region. I have a paper that you can look up. It's called "To Krig or Not to Krig." It's in JCP, but so how you fill up GAPI regions either with POD-based GAPI, something called GAPI POD, or with kriging. And turns out kriging is really good.
Yeah, because I truly think that we're going to have a lot of like gaps in the data in the velocity field when we actually run these experiments. So being able to get as good enough of an initial guess is going to be important.
So what kriging is, it's kind of you don't interpolate directly the values, right? You construct an operator, and then you sample the operator. It's called also GPR, Gauss process regression. So it can also give you uncertainty and so on, but it is that's the way to. That's how I fill up gaps.
Good, that's good to know, because that's filling up gaps is going to be something we need to do.
Yeah.
Michael, I also have a quick question. So since the fish is moving, right? So at different snapshot, so how do you distinguish the point, the training point for the pin, whether the point is inside the fish or outside in the flow field?
Yeah, so basically what ends up happening is the way that I've done it is I basically know like all points inside the fish's body at each time step, and those are just removed from the quote unquote grid. So you'll never sample from a point in the domain that's inside the fish's body.
Also, every step you sample from basically different data domain, right? You have a different data domain.
Yeah, that's basically what's happening. Yeah, because it's so like for this time step, like this point, for example, is not included in the domain. But at the next time step, the fish's body will have passed through it, so you can have a velocity vector there.
Okay. Basically, you have to pre-process this data, like to remove all these points.
Yeah, that's basically how I've done it.
Okay. And also for the experiment, basically you learn the pressure, right? For the experiment of the fish turn around, you learn the pressure. So did you find what happened? What the signal that gave the fish so that fish make a turn before it reached?
Yeah, so
there a pressure
that's the next
signal?
thing to do is now that we have this pressure field, let's try to understand it, right? We haven't done that yet.
Oh, okay.
But that is right. Like what motivated it to turn? And who knows? It might have been something in the flow field, or it might have thought a particle was food. So it's sometimes. Okay. I'm surprised they actually got the fish to turn, because I'm running.
Yeah, because we didn't see anything weird, right, in the pressure.
It's been temperamental. Yeah, no, I haven't. I didn't see anything like that would suggest why it turned.
Yeah, and also for the other example, when the big fish is following the small fish, so is that actually just a mechanical signaling, or is because of there's a fish in front? So for example, if I have a paddle fluctuating in front, is that big fish is going to follow, or just basically is going to ignore it?
Yeah, so this is actually a mechanical flapping foil.
Oh, it's a foil. Okay.
In the front here.
It's not a fish. Okay. So.
The idea is that the vortices being shed by this foil, the trout is responding to. And right. So we've actually, if you actually watch the video, like of the full experiment, the trout would be somewhere here, be moving around the tank, and then finding this spot, and then staying there.
Oh.
And so the question is what made them want to stay right behind the foil? Yeah. And in fact, be at the same frequency as the foil is moving.
Right. There was a paper by Michael Triandafilou and Lauder in Science years ago. Yep. They had that actually, not a foil, but like a just a pole generating vortices.
Right.
And then there was a dead fish behind.
And
And
then swimming.
the dead fish would go between the vortices. It would try to avoid the vortices. So it was a case of a dead fish swimming.
Exactly.
Really,
Exactly. Yep.
because it was totally mechanical, actually. Really fun.
Oh.
It was on the cover of Science. Michael Genophilos is my collaborator, so he has a big poster from the cover of Science. It was, Heli, since you like covers, they were on the cover of Science.
Okay. Okay, thank you very much.
You're welcome.
Do we have more questions for Michael? If not, thank you, Michael, for this wonderful talk. And as already
you.
George mentioned, this was a very thorough study. Thank you.
Yeah, excellent, Michael.
So we move on to our second speaker, Shanda Lee. So he would be talking to us about a topic, is L2 physics-informed loss always suitable for training physics-informed neural networks? And a little bit about him. He is a first-year PhD student in machine learning department in the School of Computer Science at the Carnegie Mellon University. And he's advised by Professor Yiming Yang. He received his bachelor's degree from Turing class, Peking University, where he worked with Professor Liwei Wang and Dr. D. He. His research interests include developing deep learning architectures and algorithms for various applications, exampling, solving partial differential equations, graph representation learning, etc. With that, let's welcome him for the presentation. You may want to share your screen, Shanda.
Yes. Can you see my screen now?
Yes.
Okay, great. And thanks for the introduction. I'm Shanda Li, and it's my great pleasure to be here and talk about one of my recent work on the loss design for physics-informed neural network. So this work was done when I was in Peking University, and my co-authors are Chuwei Wang, Di He, and Liwei Wang. Chuwei Wang is a senior undergraduate student in Peking University, and he's going to apply for a PhD position now. And he's also in our discussion today, so he will be participating in our discussion after my talk. And Di He and Liwei Wang are faculty members in Peking University. Okay, now, so let's get started. To begin with, I will briefly introduce the background on partial differential equation and deep learning. I guess in this group, everybody should be very familiar with the related background, so I will move relatively quickly. So partial differential equation is very important in mathematical modeling of many different applications, and solving partial differential equation is an important task to understand these different systems. In recent years, deep learning has achieved huge success in various domains like computer vision, natural language processing, and graph-based machine learning. So an interesting question is, can we use deep learning to solve PDE? And in this talk, we consider PDE in this form. So it involves a equation, a differential equation where the L is the partial differential operator and some boundary condition in the boundary of the domain omega. So the goal is trying to find some function u that satisfies this system of equations. And one of the seminal work in solving PDE with deep learning is physics-informed neural network, or PIN for short. So in my opinion, PIN considers solving PDE as a function approximation problem. So PIN trains a neural network to express the PDE solution with the so-called physics-informed loss. So this loss is induced by the differential equation, and it composed of the residual loss, which is can be viewed as the L2 norm of Lu minus phi, and another L2 norm of on the boundary. So here we use a neural network U theta, where X is the input and theta is the parameter. Since the loss function, the L2 physics-informed loss involves calculating the norm in a high-dimensional space omega. So typically we approximate the loss function using Monte Carlo samples. So we sample like N1 data point from the domain omega and N2 data point from the boundary, and compute these two loss function and try to solve the optimization problem. So this is described in the original PIM paper, and it's like in mean squared error loss or L2 loss, which is used as default in PIM training. Okay, as you can see, PIN is very elegant and successful, and we want to use it to solve high-dimensional PDE. We work on high-dimensional PDE because on one hand, conventional method usually fail on high-dimensional cases due to the curse of dimensionality, and on the other hand, neural networks do well in representing high-dimensional mapping. Theoretically, they are universal approximator even for high-dimensional functions, and empirically, they have demonstrated significant and powerful. They have demonstrated that success in learning high-dimensional mapping in computer vision and natural language processing. So we want to apply PIM to high-dimensional PDE. But in some preliminary experiment, we find that PIM's accuracy is not satisfactory on some of the high-dimensional nonlinear PDE, like HJB equation we will describe later. And this observation motivates our research. So we will move on to the main parts of our talk today. And first, I will present how to understand PIM or PIM training through the lens of stability. So again, in default setting for training PIM, we use the L2 physics-informed loss described here. And it's trivial that if we obtain zero training loss, then the learned solution U must satisfy that LU equals B and BU equals psi. So the learned solution is exactly accurate. However, practically, it's not realistic to get zero training loss. Usually, we only obtain small but non-zero training loss. So an important question to ask is, does a learned solution with a small loss always corresponds to a good approximation of the exact solution? We believe that it is one of the most important and fundamental questions in theoretical analysis of PIM. So ideally, we want that if the training loss, like these two terms, are small, then the distance between the learned solution U and the ground truth can also be small. So in this case, we can learn solution with provable guarantee. Now let's take a closer look at the learned solution. So the learned solution U theta x, we can see that it's actually a solution to a perturbed PDE. So it's here, so it's LU equals LU theta and BU equals BU theta. And we can rewrite this equation like this. So these two are the original PDE we want to solve. And these two terms can be viewed as the perturbation. And during the training of PIM, we are actually somehow minimizing the scale of perturbation because the scale of the perturbation is measured by the physics-informed loss. Like we use L2 loss, then we measure the scale of this perturbation using the L2 norm. So when training PIM, we are minimizing this kind of perturbation and obtain a learned solution, which is the solution to a slightly perturbed PDE. So if we want the learned solution, U theta can approximate the ground truth well. We must expect that the solution is, the PDE is stable. To be more concrete, we say that An equation is stable if the solution to this perturbed PDE converge to the exact solution as the norm of the perturbation approach 0. So when the perturbation is small enough, when it goes to 0, we want the solution also goes to also converge to the exact solution. That's what we call stability in the context of PDE. And to be more concrete, we reformulate the notion of stability in the context of PIM. So we say that given this partial differential equation, we say the equation is Z1, Z2, Z3 stable if the distance between the Larn solution U and the ground truth U theta, U star, the distance goes to 0 as these two terms, the Z1 norm of this and the Z2 norm of this goes to 0. So here Z1, Z2, Z3 are 3 Banach spaces. And as you can see, Z1 and Z2 corresponds to the PIM loss, and usually Z3 should depend on the application. So how we measure the distance between the Larn solution and the ground truth. So if a PDE is Z1, Z2, Z3 stable, then we can design physics-informed loss function correspond to the Z1 norm and Z2 norm. In this case, we can obtain a Larn solution U theta that is probably close to the exact solution if the training loss is small enough. And let's go back to the default setting of PIM. So by default, PIM training uses L2 physics-informed loss. So this choice is suitable when the PDE is L2Z stable for some Banach space Z. So in this case, the notion of stability actually offers us a way to investigate the loss design of PIM. And when we work on some equation, we can investigate its stability property to see whether L2 physics-informed loss can be the right choice. Okay, now let's move on to the next part. We will use the notion of stability to analyze why PIM fail for some high-dimensional HJB equation. Let's briefly talk about the HJB equation. It's Hamilton-Jacobi-Bellman equation. It's one of the most important high-dimensional PDE in optimal control, and arguably one of the most high-dimensional PDE. It establishes a necessary and sufficient condition of a control optimality regarding the cost function. And if you are familiar with optimal control, the solution to the HJB equation is the value function in the optimal control. And we work on a class of HJB equation described here. I don't want to go into detail, but I point out that the class of HJB equation we study here is representative in high-dimensional nonlinear PDE, and it covers many interesting applications. So we want to study the stability property of HJB equation to see whether the loss design in PIM is suitable to solve this kind of HJB equation. And this is our first theoretical result. We proved that the class of n-dimensional HJB equation is LP, LQ, W11 stable if P is greater than N and Q is greater than Kn, where K depends on the equation. So we're saying that if we want to use LP loss for training PIM to solve high-dimensional HJB equation and set P to be sufficiently large, then we are good. We can obtain a Larn solution with provable guarantee if we can minimize the training loss. So here is the formal statement of this theorem. It says that, again, it says that we need to set the P in the LP loss sufficiently large. However, this theorem does not say anything about whether L2 loss can be the right choice for solving high-dimensional PDE. And we have another theoretical result on this. So the class of n-dimensional HJB equation is not LP, LQ, W11 stable if P is not large enough, particularly if P is smaller than n/4. So in this case, if we want to solve n-dimensional HJB equation and use L2 loss, we cannot guarantee to obtain an accurate solution. And let's take a look at the formal form of this theorem. So for arbitrary positive epsilon, if P is less than n/4, we can always find a smooth function U such that the corresponding LP physics-informed loss is very small, is smaller than epsilon, but its distance from the ground truth is arbitrarily large. So these results actually indicate that the distances between the Lorentz solution U theta and the ground truth U star and their gradient, like the gradient of U theta and the gradient of U star, the distances can be arbitrarily large, even if the L2 loss is small. And in this case—
Can I ask a question, Shanda?
Yeah.
Where do you use, for example, if I have a Fokker-Planck equation, is that the theorem still valid, or where do you use the properties of the Hamilton-Jacobi-Bellman equation here? Are you using this for the derivation of the theorem, or is it particular to HJB, or is it, let's say, high-dimensional Fokker-Planck?
Yes, actually, we use some property of HJB equation. So actually, we work on equation in this form. And I guess our proof technique can be extended to some other high-dimensional equation, but we don't have work on it. And I think they can be future work, but
no, but Fokker-Planck is high-dimensional and linear.
Oh, so for linear equation, I guess L2 loss may be sufficient, but I cannot check.
So it's the last term. It's the last term that causes the problem.
Yes, I think so.
Okay. I mean, somehow in the proof, you should be able to see what that causes that problem.
Oh, yes. So we work on this form of equation, and yes, this cause some problem for the L2 norm, for the L2 loss. And for now, the scope is restricted to the above equation. And for other equation, I think yes, we need to treat the equation differently. And I guess for linear equation, L2 loss is okay for linear equations. Okay, so let's move on.
Sorry, I have another question. Here you assume the boundary condition is exact, right?
Yes.
What if the boundary condition also can have small error?
If the boundary condition also have small error, then I guess here the error can be even larger. We force the boundary condition to be strictly satisfied to make it easier to find a counterexample. But if there are some error here, like we can set U as U plus delta. So here, so this does not change.
Oh, I see. So basically, you construct an example, right, to prove this.
So
yeah,
we always
because,
find
I see. Yeah, because currently actually we have project on HJB equation, and we use L2, and the accuracy is probably 1%. It looks good. Okay, I see.
Shanda, sorry, Lulu. Go ahead. Go ahead, Lulu.
So I mean, during the training, actually in practice, actually sometimes the ping may still have good solution.
Yes. So sometimes pin yes, pin sometimes can have good solution, but this is like a counterexample. So
Okay,
it's
I
possible
see.
that we find some function u, its loss is small, but the error is large.
What if let's say we have extra constraint on the let's say Lipschitz smoothness or Lipschitz constant on the function instead of C infinity? We have some bounded slope or something.
Like I'm not sure, because I think it's a good question, and I think, but now I'm not sure, because actually the neural network we use is universal approximator. So
Yes, but during the training, actually, it cannot explore this entire C infinite space, because we start from smooth initialization, then during SGD, somehow
yes.
the smoothness is always guaranteed. So actually, the space actually is much smaller than in C infinity.
Yes, okay, I agree. So yes, I agree that if we can add more constraint, like we force this solution U to be Lipschitz continuous, we can get more realistic result. But for now, we only consider it a C infinity.
Okay, thank you.
And Shanda, basically the informal version of your theorem says that L2 is good up to 7 dimensions.
Yes, actually in the experiment, we work on like 100-dimensional problem.
Okay. All right. I think, Handy, you had a comment. Maybe you can make your comment so everybody can hear it. He put it on the chat about the smoothness of the solutions.
Okay, it says solutions to SJB are usually not smooth without bounded second-order derivative and even first derivative, and solutions can be singular. And subleft space without weights does not seem a practical framework to use. Okay, so here we consider subleft space like W11 here, because first we want the distance between the Lorentz solution, the function value U theta and U star are close, and we also think that the gradient of the solution to the SJB equation is closely related to the optimal control function. So we want it also close to the ground truth. So, and we choose like WM, the subleft space here.
Yeah, just a follow-up comment for the Handy's comment. So actually, I think Handy could be is right. So the kind of HGB equation we are solving, actually it has singularity at x equals 0. So when x equals 0, the solution blows up, goes to infinity. Then we did some trick to solve this using pins. We do not directly solve the pins using the solving the HGB using pins because it's a singularity issue.
Okay, I see. So in our experiment, we just construct some cases of SJB equation where the solution is smooth, and so I guess this does not encounter in our study, but yes, I think for a more general framework or theory, I think it's good to take this kind of singularity into account, and I think it can be important for future study.
And just the last point, since we broke here, I think the paper by Maja Raisi, my former postdoc, he did either 200 or 400 dimensions. Lulu, do you remember? He's
yes, I remember. Yes, really
solo author. But I think that's Fokker-Planck.
400-dimensional HJB?
I think it's Fokker-Planck.
Okay. Using pin?
Yes. It's one of the first papers by Maja Raisi when he was in my group, single author.
Oh, I will definitely check this paper.
Yes, this is Jerome Darbon from Brown. I agree with George, but I mean, just to comment, I mean, those stability results, they depend a lot on the initial data. So on the domain and the initial data. So you are working, so my understanding, and correct me if I'm wrong, is that you are exhibiting a class of Hamilton-Jacobi PDE for which you do not have the stability involving L2. Am I correct?
Oh, sorry, I don't.
You are exhibiting class of Hamilton-Jacobi PDE for which you do not have the stability in L2.
Yes.
Okay.
Okay. Thanks for the comment. And so I will move on to the next part.
Can I make a supplement here regarding George's equation about the Fokker-Planck's equation? I think for linear equation, it doesn't suffer from issues of this source because, for example, we have some parabolic a priori estimation for the well-posedness of linear equations, and in most cases we can prove stability for L2, and for example, we choose L2 physical informed loss, we can achieve, for example, H1 or even H2 stability. So I think it's okay for linear equation.
Great, thank you. Shanda, you can continue, please.
Okay. Thanks for the comment. And so I'm going to move on to our algorithm for solving this kind of high-dimensional HJB equation. So again, let's recap the theoretical analysis. Our theory shows that when n is super large, like 100, then L2 loss may not be the right choice for solving high-dimensional HJB equation. Although in our discussion, we feel that this result, we have more detailed discussion on this result, like the having more restrictions or like something like that. But the first result do tell us that if we set P and Q sufficiently large, then we can train high-dimensional HJB equation. We can train Penn on high-dimensional HJB equation and learn some solution with provable guarantee. So this motivates us to use L infinity physics informed loss in Penn training. And here we arrive at a new training objective. It's L infinity physics informed loss, and it's like the Superman in the domain for the residual and the Superman on the boundary. As you can see, if you want to minimize this kind of loss function, L infinity loss function, we actually arrive at a min-max optimization problem. And this kind of formulation is very similar to the problem in the adversarial robustness, where we want to minimize the training loss on the adversarially chosen data points. So our algorithm is like a bi-level optimization, and in the inner loop, we first sample some data point, and we perform a few gradient-based updates to obtain data point such that their point-wise loss is large. And in this case, we can approximate the Superman. And in the outer loop, after we obtain this kind of adversarial data point with large point-wise loss, we fix this generated data point and calculate the gradient G to learn the network parameters. And this is the detailed formulation of our algorithm. I will carefully describe it. So first, in each training iteration, we sample some data, like N1 data from the domain and N2 data from the boundary. And then we perform a few like gradient ascent for the data point so that we obtain some data point whose point-wise physics informed loss is large. And after that, we obtain some like adversarial data point. We use this data point to compute the physics informed loss and compute the gradient to update the neural network parameter. So this is our L infinity training for PIN, and it's like adversarial training. And we show that
I'm sorry,
using
excuse me, Shanda. It's Zongren from Brown. Can I ask a question about this algorithm?
yes.
Yeah, so the reason why you use adversarial training instead of regular training is because you want to minimize the L infinity rule, right?
Yes.
So could you go back to the previous slide?
Yeah. Okay.
So you don't have supremum here, you don't have to do adversarial training. I mean,
Sorry?
you can. Okay, so this is my question. That have you tried not to do this adversarial training and by sampling regularly, randomly data points, and you take the maximum of the loss among all of the data points, and you minimize using that one? Have you tried that? So
yes, this is a very interesting question, and I think yes, we can do this by sampling a lot of data point and find the data point whose training loss is very large and use this data point in this training iteration. But in this case, I guess the training would be inefficient because there will only be one data point that contribute to the final loss function. And another thing is we have tried another experiment. We have worked on like LP physics informed loss with large but finite P. And I will discuss this method later.
Okay, so like most people think like this maximum, it cannot be back propagated, but actually in practice, a lot of people are doing that. Like it works like max pooling, so we can do back propagate through this. Okay, thank you.
Okay, thanks for the question. And again, what I'm trying to say is, yes, maximum can be back propagated, but in this case, there will only be one data point contribute to the loss function. And I guess this may make the training inefficient because in that case, is somehow the batch size is 1.
Yeah, you're right. Thank you.
Shanda, continue. Please continue. Probably you have all the answers.
Okay. So we apply our method to solve high-dimensional HJB equation, and we evaluate the quality of the learned solution using L1 relative error, L2 relative error. These are common evaluation metrics. And we additionally evaluate on W11 relative error because first of all, we said that the gradient of the solution is also important in optimal control, and our theory claims W11 stability. So we're working on like very high dimensional case. So we will set n to 100 and 250. And we can see that our method do significantly improve the accuracy of baseline models like original pin and some other modifications. And we also like visualize the learned solution of pin and our method. This is taken in a 2-dimensional snapshot, and we can see that our solution has much smaller point-wise error. And we also visualize the gradient norm of the learned solution of pin and our method. Again, our method can learn the gradient well. Okay, so that's our main experimental result. Now I'm going to discuss another interesting question or another alternative approach that is not using adversarial training. We just minimize LP loss with large but finite P. However, it turns out that doing this does not lead to satisfactory results. And at the first glance, this result seems to contradict our previous theoretical finding. But actually, we find that minimizing LP loss with large but finite P can lead to some problem during training. First, we need to approximate LP norm. And if P is large, the Monte Carlo variance will be large. So we need a lot of Monte Carlo sample, and the sample can be inefficient. And secondly, when the P is large, the optimization landscape can be very stiff, and it can lead to some optimization difficulty. So in this experiment actually show that although our theory indicate that LP loss with large but finite P can work, but practically it does not lead to satisfactory result, and possibly it's due to like sampling efficiency or optimization difficulty for this kind of loss term. And I hope this experimental result answer Dongren's previous question. Okay. So now it's time to wrap up and summarize the talk today. So I have some take-home message, and the first is L2 loss may not always be the right choice to train pin, and although I guess we may have more theoretical investigation on the how or when this statement can be applied. And secondly, we advocate the notion of stability since it can offer principled understanding on the loss design of pin. And finally, from the experiment point of view, we propose an adversarial training-based algorithm. It can minimize like L infinity physics-informed loss, and it turns out to be practically powerful. And some possible future directions, we can analyze the stability properties for other important PDE, like just Chue has just mentioned for like high-dimensional Fokker plant is a linear high-dimensional equation, then the L2 stability can be guaranteed. In this case, L2 physics-informed loss would be okay. And it's also an interesting direction to design more efficient algorithm for L infinity training, since currently we are using adversarial training, and one of the problem is it's very time consuming since it introduced a lot of computational overhead in the inner loop. And that's all for my talk today. And our paper, our code can be found on the web, on the internet. And this work has just been accepted to NeurIPS 2022. Thanks. And any questions?
Thank you, Shanda.
Thank you, Shanda. That's very good, excellent talk. I put on the chat a paper we wrote on meta learning the loss function. So
meta learning loss function.
Yeah, so you go in with an open mind and you and you actually learn the type of stuff. But your work is excellent. Thank you.
Thanks.
Questions for him?
Lulu, Jerome, Handy, do you have any questions? Or he disappeared maybe.
This is Jerome again. Do you have any, let's say that I want to have error of epsilon, for the solution. Do you know how many data do I need to reach that epsilon?
Okay.
What I'm saying is that what is the trade-off between having epsilon in this L infinity norm with respect to the data that you need to sample?
Oh, yes, I think this is a very good question. But I think our current theoretical framework does not cover this because we only focus on how we can approximate the solution if the loss is small. But if we want to talk about sample complexity, we may take the training algorithm like the neural network and the SGD into account. So I think I agree this is very important direction to study about the sample complexity, but I guess our current theoretical framework cannot answer this question.
Okay, thank you.
There's some work by Katsoulakis at UMass Amherst, the mathematics department, on interpolating norms for adversarial training. I don't know if you have seen that and if that's pertinent here.
So what?
It's interpolating norms.
Interpolate.
Gamma divergence and other.
I'm not familiar with that.
I think there's a guy called Nielsen who has spent all his life looking at different norms of minimizing things in different norms and so on. So that now becomes. Yeah, but this is the name of the guy is Katsoulakis, Marcos Katsoulakis at UMass Amherst. Let me look him up.
I will search that.
Hey, do you mean by interpolation norm?
They can go from like gamma divergence and this type of. He's using it for adversarial training for guns, for example. So here's some theoretical results. So I cannot remember exactly what the benefit is, but maybe Jerome, do you remember?
Vaguely, I remember vaguely, George.
Okay.
I don't want to.
Yeah. It is for adversarial training, and they show, even for guns, they show better results using this other interpolating norms.
Yeah.
Okay. That sounds interesting.
So if we don't have any more questions for Shanda, we'd like to thank him for tuning in today and giving us this wonderful talk. And thank you everyone for tuning in, and we'll share our recordings on our YouTube channel. And all the people who have subscribed to our channel will receive a notification. Thank you. Have a nice rest of the day.
Bye-bye. Thanks.
Bye.
Thank you.